So pressure vessels are used everywhere in engineering applications. They're typically cylindrical or spherical, and that reduces the number of weak points. It distributes the stress evenly throughout the structure. A spherical pressure vessel is ideally the best one to have, but we go with cylindrical because they pack better, and because especially for cans, if we were all engineers, we'd make our cans spherical, but they are the cans that we all brought today, hopefully today. Oh, why not? Here we go. I got the adrenaline shot. Smart energy. I never do these energy drinks. So if it wasn't for this class, we got a Sprite can, LaCroix, Mountain Dew, awesome. Oh, AHA, sparkling water. Okay. Zoe, which one do you have? You didn't bring one? Okay. So I did a little bit of research on how these aluminum cans are made. And also I discovered that there's a shortage of aluminum right now because during COVID, everyone is staying at home and drinking beer and sodas and not going out to restaurants where they can get them out of fountain machines. So during the shortage, there's, I guess, two big companies that manufacture mostly the aluminum used in cans. And they're building new factories and doing things like that to make up for the shortfall. But the aluminum that is used in these cans is 3000 series. It's 3004. What are the properties of the aluminum that's used in cans that's important, do you think? The material properties. What do you want out of this can? Ductility? Yeah, you want high. Homogeneous. Okay. Isotropic, maybe. So when we draw it, it kind of evenly flows everywhere. Okay, these are all good properties. What else? What else do we want out of this aluminum can? Think of the other properties of a material that you would want to have in the aluminum here. Don't you think strength is still kind of important? Yeah. Right? You still want it to be strong. So there's this like trade-off between ductility and strength that we have to deal with here. You probably also want it to be what do you call it for food? You want to have it. Sorry? Food safe. Food safe. So maybe you don't want it to leach out anything into the drink or something like that. Cost is always important when you're manufacturing and these things. So they spray the interior with like a lacquer or some sort of epoxy to keep the metal taste out. It's not just like natural light that does that anymore. It's pretty much all aluminum cans. Also, does anyone know why they dimple the bottom of the can like this? So they stack? Yeah, that's true. They stack. Any other reason why? so that they look larger when they're really not. You get less soda in it. Maybe. What else, guys?
I'm guessing it's so that they can induce points where there's going to be like the high stress. So they know if it fails and where it should fail at.
So you think like around here is probably going to fail first, right?
Exactly.
Uh-huh.
So they strengthen that area. Just
Okay.
So they can like ensure that it's not going to fail like randomly.
Okay. Okay, for sure. Yeah. Yeah, I'm sure this is, it could fail around the seam up here, but maybe it's going to do it up here.
Also, so that when the pressure's on it, the bottom of the bow.
Yes, exactly. This is like an architectural feature, you know, it's like an arch on a bridge. It's not just flat on the bottom, it's dome shaped. So the you know, forces push against the aluminum here. And also in the bottom, turn your can over and look at it really carefully. Do you see an impression in there? Run your finger over it. Feel it. You feel something, right? What is that? Every aluminum can in the world has that. What?
Mold number.
The mold number. Yeah, exactly. Yeah. Well, there's two numbers. There's there's the tool that's used to draw it, I think, and then there's a tool that's used to do the dome print on the bottom. And so yeah, that's right. And so it's very thin, right? It's very thin. So what kind of stresses can we assume that are occurring on this can? Thin wall. So what is the criteria for a thin wall vessel?
Radius to thickness is greater than 10.
Yes, that's correct. So the thickness of the aluminum is compared to the radius of the cylinder, right? So it has to be 10 times thickness. So with that, then, what exactly is biaxial stress? Stresses, what are they? Sorry? Hoop and longitudinal. So what is hoop and what is longitudinal? Uh-huh. Yeah, that's right. That's right. So this is longitudinal going, let me see if I'm left anyone out of that.
It is on the.
Sorry, I had to let everyone else in. Okay, so hoop and longitudinal. So hoop got its name from the metal hoops that were used in the barrels, the whiskey barrels and wine barrels, I guess, to hold them together. And so that's what we're going to assume when we do our testing here. So there's two things that you need to know in order to calculate the internal pressure of the can, and that is the elastic modulus and the Poisson's ratio. Okay, so for the elastic modulus, you can look this up yourself, but because this is a 3004 series or 3004 aluminum, it has an elastic modulus of about 70 gigapascals and a Poisson's ratio of 0.33. Okay, and so we can get, there's a separate calculation for the hoop stress or the longitudinal stress, but what do we think that the stress longitudinally as compared to hoop is going to be when we look at the strain gauge data? Which one is going to be, how are they going to be proportionally different, the stress? Which one's going to be greater? Hoop is going to be greater by how much? 2 times. Yeah. The hoop's going to be twice as much as the longitudinal stress. So what we're going to be doing is some of you are going to be putting in on your strain gauges longitudinally, and some of you will put them in the hoop. And we're going to be able to, we're going to only be able to collect the data on one strain gauge at a time right now. Hopefully I'll get it sorted out so we can do 2. But since the data collection is so fast, it's the only difference is that, yeah, you're using the same aluminum can, so hopefully we can compare apples to apples here. But one thing is just by how much you squeeze it a little bit when you open it, it can really impact the reading. So let's try not to handle it too much when we're opening it. A couple of other little fun facts about the aluminum is the tab that's on the top. So remember when have you ever used those tabs that just kind of like tear off? Yeah. So all cans used to be the tear off type, and before they came up with these ones that actually stay on.
Still like that.
They're still like that in most of Europe. Can you believe that? Holy cow, because people just throw those on the ground and then they end up in the sand and then people step on it and they cut themselves. So they're terrible things to have. But these are ingenious the way they work. Does anyone know how these tabs work? What was that?
Leverage.
Leverage, yeah. Yeah, well, first, it acts like a wheelbarrow in terms of the forces that are being applied. And there's this tiny little rivet hole that's right there. And that breaks the seal. And then, so that's the first to go. And so when you see a little bit of spray happening, it's right out of that little rivet hole. And as soon as the pressure is out of the can, then it acts like a lever on the end here and is able to actually tear open the hole, but not until the pressure is released can it do that. So it's pressure release first, and then the outer edge here pulls it open, and then you can do it. So I when I left Cal Poly, I got accepted to the Colorado School of Mines, and all my research, I said no to the proposal, but Coors was going to fund all of my research to work on these aluminum tab tops and come up with better dies to press. It was like a laser coating in the dies that they used to cut these things out. It would have been a good project, but because the Golden, Colorado is right there, the factory's right there, so would have been a good one. And what? I know, it would have been amazing. I ended up going to Purdue, and my friends at Purdue were like, "You're crazy, man. What the hell did you want to come here to freaking Indiana and do that when you could have been sponsored by, yeah." So anyway, I guess, oh yeah, so ductility, right? We said ductility is really important, probably the most important. These things are drawn so thin, and we're actually, after we're done with it, we're gonna tear the can open, and we're gonna measure the wall thickness, because we need to do that to get our pressure calculation. But it's like 75 microns or something like that. And but what do you think, what type of aluminum makes a very ductile aluminum cake? What type of aluminum would make a ductile one? Like aluminum foil, Reynolds foil, it's drawn down incredibly thin. No. Hey, what is important? It's purity. Yeah, you want to have very pure aluminum. Any sort of pure metal is going to have a lot of ductility. to it. Once you start adding alloying elements, that's when you start getting a stronger metal, but then you lose ductility. So it's a trade-off there. So 3004 aluminum has only about 1% of the major alloying element, which is manganese and magnesium. Only about 1%. So these are, they don't have the, precipitation strengthened properties that like aircraft aluminums have, really strong aluminums. It's a solid solution, strengthened, just only very, minor amounts though to maintain the ductility. So yeah, it's a series of draws. I think they first make like a little cut puck, and then they draw it thinner and thinner, and it's actually extruded. So it goes into a die that has a very thin, cylinder in it, and the aluminum just keeps pushing up through it, and you end up with some ears at the top, some little waviness at the top, because you can't get, perfectly smooth walls, and so they just trim the top off it where there's a little bit of that, and then for these aluminum, for these tops on here, they have to narrow it down at the top like this, like they're doing here, and that's another die that's used to slow. There's actually 7 or 8 different dies that narrow it down here at the top, and then this top piece is folded over, convoluted, I think like twice over on itself, and then there's like a gasket, a polymer gasket that seals the whole thing.
Yeah, I was gonna say, is it like Prescott, they did use it as a seal or anything?
A seal, yeah. So your question was, do they use a sealer?
Yeah.
Yeah.
Is it just a Prescott?
No. They use a sealer in there. Yeah, there's a little bit of epoxy that's used to keep it to keep the seal tight. And so these cans are, when they're compressed like that, they're very strong. So you'll never see, correct me if I'm wrong, but most aluminum cans are all carbonated beverages, right? And it has to be that way, or else you wouldn't be able to stack them. They wouldn't be able to be shipped. They would just, crush under weight. So that's what gives these, pressure vessels their strength, is that they have to be under pressure in order to maintain their integrity. So I could, stand on this can right now, and it wouldn't crush much.
There are some cans that aren't pressurized, but
Yeah.
still sealed. So as soon as you exert force on them, they pressurize.
They still.
Oh.
Pushing back, so.
Oh, really? Okay, let's try this. Ready? Yep. No problem.
You actually stand on an empty one too,
I could stand on an empty one.
until you touch the side.
Yeah, that's true. Okay.